so this is the second video on integrals in terms of net change of a quantity for section 7.1 in AP Calculus. And this will be a relatively short video. We're just going to do the last couple of examples that are not dealing with particle motion. They're dealing with other things. So here we're given a problem where water is flowing from the bottom of a storage tank at a rate of R of t equals 200 minus 4t liters per minute, where 0 is less than or equal to t is less than or equal to 50. Find the amount of water that flows from the tank during the first 10 minutes. So this is an accumulation problem, essentially. If you accumulate all of your rates of change over that whole 10 minutes, then that'll tell you the total amount of change that you've had in whatever the quantity is. So in this case, it's in the water that has flowed out of the tank. So accumulation, if we want to accumulate stuff, that is an integral. So all you have to do to find the total amount of a quantity is to integrate its rate of change. So here we would integrate 200 minus 4t over the interval from 0 to 10. That's all there is to it. Like net change is not difficult. You just integrate the rate of change function. That's all you do. So even this one, we could do it without a calculator. 200 will integrate back to 200t, and 4t will integrate back to negative 2t squared from 0 to 10. So then we substitute our 10 in, and then we substitute our 0 in. So we get 2,000 minus 200 minus all that becomes 0. Oh, that's 2,000. There's another 0 in there. So that becomes 1,800. Now, the one thing that you will have to do then a lot of times is they will then ask you to make sure you have units on it and to sometimes explain what that answer means in the context of the problem. So that 1,800, well, our rate was liters per minute. So we had liters per minute was the rate function. So that would be R. So essentially, if we think about this in terms of a multiplication problem, we were taking R, which is in liters per minute, and multiplying it by the change in time, which is also in minutes. So that leaves us with units of liters. So in the context of the problem, you could say that this means that 1,800 liters of water have flowed out of the tank over the first 10 minutes. That's all you'd have to say. All right, and then lastly, we have a bacteria population is 4,000 at time 0, and its rate of growth is 1,000 times 2 to the t bacteria per hour after t hours. What is the population after 1 hour? Okay, so there's two ways we could do this. So I'm going to do just come up with a function first off for the amount of change. Sorry, I had to think about that for a minute. So if we're going from 0 hours to 1 hour, and our function for the rate of change of the population of the bacteria is this guy. Now, we could integrate that by hand if you remember the a to the u derivative formula. But if you want to just put that straight into your calculator, you could do that as well. Just do math 9 from 0 to 1. This would probably be a calculator problem. And you're going to get 1,442.695 bacteria. Now, what does that number represent? That's how many bacteria the population has grown by in the course of 1 hour. Does that tell me what the population is, though? No, because I have to take into consideration what the population is at the beginning of my interval. So I actually would take this integral amount and I would add the initial population of 4,000 onto it. So that would give me a total of 5,000. We'll go ahead and round it to the nearest bacteria. So 5,443 bacteria in the population there. So that's very important that if you have an initial value at your lower limit of your integral, then you add that onto your net change, because all the integral represents is the amount of change that you had, not what the actual final value is necessarily. All right, so there's one more AP practice problem there at the bottom. I want you to give that one a try. That is an initial value problem, like this one that we just did here. Be sure to think about the fact that the temperature is dropping, though. All right. So we will discuss that next time I see you.